All right, so what to do when maximum likelihood isn't your best friend? Don't make stuff up once, make stuff up a lot. That's right. Because why? Why not, right?
Put it on the shirt.
Put it on a shirt?
Put it on the shirt.
Make stuff up.
A lot.
A lot. Make a lot of stuff up. When I teach psychometrics, when you there's a field of psychometrics called classical test theory that we talk about when you add things together, and so I sort of call that the add shit up model. This is the make shit up model, all right? And believe it or not, you can impute when you add shit up. Make and add shit up. Anyway, so instead of using single imputation, a better idea is to use multiple imputation. Right? The idea is that you create a set of complete data sets, each with a different value or a set of different values for all the missing cases. Right? So no one data set likely will look like another unless there's a little tiny bit of data that's missing. The multiple imputation is a mechanism where you fill in your missing data with so-called plausible values. Makes it sound so much interesting, right? So much better. Oh, that's plausibly what that person would have said. Sure, I'll do that. So you're going to end up with multiple data sets. And then the question becomes, what do you do next? The answer to which is, for each data set, you run an analysis. The same analysis you would have run on a complete data set. But now you end up with multiple sets of results. Right? So if you have 100 imputed data sets, you'll have 100 results. So finally, after that, what you can do is take the 100 results and combine them to give you answers that should be a little bit more plausible. This process of multiple imputation is analogous to if you were to believe the missing data all had distributions that underlied it, to integrating across those distributions. Right? So basically, you're integrating through Monte Carlo. You're saying, I'm going to fill in a bunch of values, and when I take the average of all the analyses, that is like averaging conditional on each of those values being a different thing each time, right? So you'll get high values sometimes and low values sometimes, and the analysis betas will fluctuate as a function of it, but in the end, you'll get to kind of the average of where it would have been marginalizing or kind of allowing the data to be almost anything in the range that was plausible for it. So this is a shortcut to analysis that's what we call a marginal likelihood or a marginal analysis itself. So the key in all of this is for the plausible values in the missing data come from a statistical model. All right, so it's almost like you'd get with missing not at random data, but the statistical model itself, some of the ways that we use it is, well, the way it's used in practice is pretty straightforward or pretty lame. I don't know how you want to call it. The defaults are pretty easy to use. You can get much more complicated, but I'll show you some of the defaults. So the key to all of this is that we're assuming all this with multivariate or with statistical distributions. Now, the most often used assumption in multiple imputation is multivariate normal. It doesn't always have to be the case. In fact, the method I'm showing you today, you don't have to assume that. It's okay. A lot of the methods out there do multiple imputation via Markov chain Monte Carlo, and the easiest ones like PROC-MI and SAS want multivariate normal because that's a really easy thing to do Markov chains with. What we're going to be doing is a Markov chain, but it's not necessarily the Monte Carlo process. It's like a series of Gibbs samplers. And then we're going to match. So we're going to kind of pull things together in what we do for how we make this work. Questions? So we're going to make stuff up, make a lot of stuff up. All right, so the missing data are filled in a number of times. All right, so here are the steps. Number one, it's the imputation phase. You make stuff up. Maybe you make it up little m times. And if you look at like the history of missing data since the field started in the 70s and 80s, some of the seminal works have like m being 5. Yeah, I'll create 5 values. 5 is way better than 1, but that was back when like computers were less powerful than the phone that you probably have in your pocket, right? Or your Apple would be like a supercomputer back there, right? So now we can make up lots of stuff, right? So the homework assignment, homework 5, is a missing data issue. You will be generating 100 data sets rather than 5. You probably could do 1,000. I don't care. Don't do 1,000. Stay with 100, otherwise the results won't be exact. So, but yeah, basically it's real easy to generate data these days. Real easy. So you create those M data sets. You analyze the data sets with the model as if they were complete. So each data set's complete. You use the analysis model on it that you would for you're planning on doing for your analysis. This is called the analysis phase. So there's imputation analysis. And the last phase in it, it's called the pooling phase. Basically, you take the M analyses and you figure out what the average, kind of the average beta would be for each effect, or whatever the parameter would be, and then a pooled standard error. And that pooling has to take into consideration both within data set standard error and between data set standard errors as you go forward. So there's a little bit of a catch in the pooling process. The things I'm going to show you have built-in pooling estimates for it. Problem is, a lot of the methods that you see out there, you sort of have to build your own pooling thing right now, which sucks. I wanted to give you the GLS function with multiple imputation, the multivariate problem, and I found that to give you a pooling estimate for that, either I'd have to create one that I didn't have the time to do, or you'd have to do it yourself, and I wasn't about to get you to do that. So that is really bad.
So when you say create it yourself, does it mean like each time you have a data set with missing data, you have to create a totally different one, or is it kind of a one and done?
Well, if you're using, let's say you're using GLS to do this. SAS or R will create the missing data no problem for you. And where it breaks down is getting it to analyze the missing data for all the data sets that you create. You probably can get it to do that, though. Where it further breaks down is where you take all those data sets and combine them into one final analysis that has one parameter estimate and one standard error. Those final parameter estimates comes from the 100 data sets, and the standard error comes from the 100 standard errors plus the standard error of the parameter itself across the 100 trials. So that last step is harder to do. It's not, I mean, the equations for it aren't exactly super complex. It's just that the problem is, like in R here, we generate an object that's a special type of object in R. So getting access to it, figuring out its properties, and figuring out where the data or where the results might get used is a little bit hard. At least it was for me to build this for you for this homework. So I would have loved to have a package that you could have built for it, but I'm really giving you a very limited version of this for homework. Does that answer your question, though, about where the problem is? So actually, I'll go a step further. If you're let's pick an analysis that no one uses, multidimensional scaling. Anyone ever done multidimensional scaling before? It's excellent. It's a fun thing. Not really. It's kind of has its own problems. But let's imagine you have missing data. You overcome it, but you have this MDS package in R. I don't even know if one exists. I'm guessing it does. And you want to use it with missing your multiply imputed data. You have to go and build that part of these two steps, the analysis part and the pooling part, to get the right results. So there's an extra step or two involved. Other questions? All right, the key to all this is our distributions. So think of it this way. The missing data, each observation that's missing, has a distribution of likely values. That's where the plausible value comes from. Some of those values are more likely than others. How on earth do you figure out what that distribution is? Here's a step. Well, yeah, I'll come up. I'll show you in just. But think about it. Think about how you'd create a distribution for what that would be. But that distribution is important because it's going to reflect how much certainty you have about what that observation happens to be. Right? Now, so going into that, I mean, I'll sort of give you the hint. If we're using like a regression, that kind of a conditional mean imputation or conditional mean imputation with error, that gives you a distribution. Right? Each predicted value, you know the mean of the prediction, you know the standard error of the prediction. You can come up with a normal distribution around. There's a distribution of response. Key to that is how good the distribution happens to be, if it gives you the right answer, And all the things that you hear about in regression apply, right? Like missing data, if you're making this regression but you omitted the variable, there's a bias. Well, there'd be a bias there, right? So you really have to get the distribution right. You have to get the uncertainty right to make this go. The other thing that can happen is that you can use variables outside the analysis you're intending to use to help you get a better sense of certainty about what to impute. Now, it's a little weird philosophically, because if those variables inform about variables in your analysis, shouldn't they be in your analysis also? Right? You'll see that happen. You'll have like an imputation set of variables, and then like the analysis set's a subset of those. And it's harder to justify. I think generally speaking, people do, but I like to think if you're going to do an imputation, if you're going to use like 20 variables to predict what an outcome should be, why aren't those 20 in the big model also, right? They weren't important for it, but it's important in this one. So it's not really telling you the whole story. So by contrast to multiple imputation is different than single imputation because you're not just making it up, you're making up a lot of stuff. No, really, it's the uncertainty, right? You're allowing that, if you were to look at one missing data point across all of the missing multiply imputed data, you should see a distribution of values that represents the uncertainty with which it might be. Right? So you want to draw at random from that distribution, you want to plug that into the data, and then you want to look at let it vary from data to data. The thought being that you're allowing whatever uncertainty is showing up with that missing data to not get shut down by plugging in one value or plugging in a constant or something along those lines. So keep the standard errors that you want to have preserved as best you can. So here's the hard part, though. If we were to, now I'm going to flip back. If we were to go to this right here, if we were to go and plug in, so let's imagine these are our three variables, right? We've got people missing on all three, right? So we go in, we say, okay, I'm going to go and predict everybody who's mixing the oxygen variable. I'm going to go give them a predicted value by using this regression. I'm going to run a regression analysis. Well, that regression analysis is interesting because it's assuming we know runtime and pulse for everybody. What happens to it if we don't know runtime and pulse? Same thing that happens before. We have to do some type of deletion. It's not likely to be there to be good, right? So if we do deletion, we end up using that. What happens? We get biased parameter estimates, right? But we're going to start there. Here's the process of the Markov chain. We start there. We use only the complete data. We get a predicted value for oxygen. We use that predicted value with oxygen. Now we still have missing pulse and runtime, but we use whatever's complete now with that for the next variable. We get a variable for runtime. Now we have complete data for pulse. It's going to be biased still, but it's complete. But we repeat this process over and over again, and guess what's going to happen to our bias? We're now in a Markov chain. And because the distribution of all the missing variables has a distribution with it too, as the chain starts to converge, our parameters start to move to where their unbiased values happen to be. So if we did this over and over and over, and we had a burn-in like we talked about last week with our chain, we would find that the parameters of each of these things would start to stabilize, and our distribution, or our posterior distribution for each of the variables that we're missing, would give us the results that we want it to do. So the neat thing about multiple imputation is it relies upon this Markov process. Even if they don't even describe it as such, it's a Markov process to build this. And that brings me to one of my other problems with R. That sounds great, but R doesn't do it that way. Check that. There's two packages I've seen get used in multiple imputation R. There's probably tons more, but these are the two big ones. One that's called MICE, which is stands for Multiple Imputation by Chained Equations. Chained equations are what we saw on that last slide, those three variables, three different regressions. They're in a chain because we started with one, and we went to the next conditional values on the first. We went to the next conditional values of the second, right, and kept going in that loop. The other one is called Amelia. Maybe because Amelia Earhart was missing, is that? I think that was it. I think that's why. I think I'm reading the synopsis for it. It was something to do with, like, we're going to impute Amelia Earhart or something like that. Help me out here. Those of you who, did you guys learn that in Ways class? No, never mind. I believe it has something to do with a famed Kansan, right? So, anyway. Amelia works with a little bit more restrictive. It has a little bit fewer options. Although what it does, I think it does pretty well. It's doing multiple imputation versus Markov chain Monte Carlo with maximum likelihood. Not maximum, multivariate normal. So that process I just described to you before, it will be imputing values in that chained approach, but with MCMC, and we'll just do exactly that. Mice is a little bit more complicated, but we're going to focus on it because one of the package's features it has is something called predictive mean matching, which tries to keep the data in the same area as the rest of the observations. So we're going to do predictive mean matching in mice, and I'm going to complain about R. Who wants to join me? I'm going to create my own software. What do you think we should call it? I think we'll just call it crap or something like that. Because it's going to be, there's some things it would do that's terrible, right? And there's nothing that would work, but something that would be a nice pejorative about it, like, you know, this thing breaks again, or maybe broken. Maybe that's what I'll call it. I use broken.
It's going to be a clever acronym.
It has to be.
That's 6 words you have to come up with.
That's a lot.
Crap only has 4.
Good point. Okay, so multiple imputation via chained equations. The key is we're going to create a set of univariate regression models. I'm going to have an example here where we take some of the data from the statistics, or the lecture 2 or 3 weeks ago that we talked about GLS for the first time, and we're going to create the equations with it. So for each variable with missing data, it's going to create a regression line that's going to try to predict what that missing value should happen to be. All right. So the process starts randomly in that it imputes values for all missing observations. By the way, for me, getting a hold of exactly how it starts and what it does was excessively difficult, like getting into the weeds of the R code, because the descriptions based in the papers that cited for mice were not sufficient for describing what it's doing. So that was one of my problems. So I believe it starts randomly. It doesn't really matter. It may just use complete versus incomplete data, which also might be. But so it starts. It says, okay, let me just complete the data by randomly drawing. For each variable in my data set, I'm just going to plug in a number that happens to appear in that variables column to begin with, right? Doesn't matter what that is right now, because if we carry this forward the right way, we'll converge to a good result. The next step is for each variable with missing data, we do this regression analysis, right? So if like oxygen was missing something, we predict it with the other variables, and using that regression analysis, we come up with the predicted mean for each person's missing data, right? So person A has missing value. We think its value should be 7.4. I don't know what 7.4 is. Just imagine 7.4 is what happens to be. That's our predictive mean itself. So with the predicted mean that we create for it, we don't just impute that value. We look at the data and we try to figure out all the other complete data cases that have a mean closest to 7.4. Right? So we take, like say, oh, look at this. We order the data from highest to lowest in terms of missing. In terms of how far off they are from 7.4. And we take a neighborhood around that, right? We say, okay, let's take the 5 closest values to 7.4. And by the way, 5 is the default in mice. It says, okay, look at everybody who has one of the 5 closest values. Now, there may be multiple people that have 5 values. So you now have this smaller subset of complete data. From that set of people that would have the 5 closest predicted means to 7.4, draw at random the missing value from them and plug it in. So now we're matching the predictive mean and we're swapping out the missing data for something that already exists in the data set. You with me? Is that weird? You can be both. It can be both. Yes, Benjamin.
So when you say all the missing data, does that mean they're all missing the exact same variable, or they're all missing, like, again, one out of the 5?
So think of it as a variable by variable approach. For the very first variable, only the people missing that we do this process for. Once we've done that, we go to the next variable. Those people who miss that variable may not be missing the second variable, but it doesn't matter. We sort of treat it as new independent process. We do the same things. We just keep looping through all the variables in the data set one at a time. So if a person's only missing one of the variables, they'll get a plugged-in value for that one. But if they're missing almost all of them except for one, then they'll get plugged-in values for the ones that they're missing as well. Each step. I'll show you in just a second. Hope that helps. Other questions? Okay. So, technically speaking, the predictive mean is only one of the methods. There's other methods that can show up as well. But what we can do is do this over and over and over again and come up with our complete data that way. So let me give you an example. This is an example of multiple imputation via chained equations and predictive mean matching. We are going to take our oft-used math example, the math data, the math performance data that I simulated a long time ago. And we're going to have three variables. We're going to have a performance on that 20-item test, the person's sex, and their college credit hours. So basically, we're going to predict, our goal in this analysis would be to predict performance as a function of sex and credit hours and its interaction. But the problem is we have missing data. In fact, here are the missing proportions. The proportion of missing, nobody's missing their sex. 17% of our data is missing the performance variable. 10% is missing the credit hours variable, and 2% is missing both performance and credit hours. Right? So you kind of get a sense for the patterns of our data that are missing. So the way this works is we don't need to impute male because we've observed all of it. Yes, debate.
Is that 17 and 10%? That 2% that's missing both, are they counted in both the 17 and 10? Or
yes, that's right. That's right. Yep. These are the same all data, just who's missing both values for it.
Cool.
Yep.
Thank you.
You're welcome. So for this, we are going to impute performance and credit hour production. And I'm going to kind of step through the first steps of the algorithm to show you how this works. Yes?
Logically, why would you bother including someone who is missing your DV and one eye? It's just like a random person on the street.
It could be, but we have their sex, and if sex is related to this, perhaps we get information about it. What will most likely happen is there'll be so much noise in it that it's not going to bias our result, and hopefully nothing happens. But yes, that is a good question, because if we have the wrong imputation model, then we might be all messed up by that as well. So we need to, good question though, thanks Lauren. Other questions? So what we need to do is impute performance and credit hour production. So we need to create a regression equation for both of these. This looks like a multivariate regression equation. In fact, we could probably do this in, well, I don't know if that's the case. It'd be a non-recursive, it'd be a recursive, it'd be a very bad path analysis because we have these things going on, but it works for our chained equations when we take them one at a time. So here for performance, we're going to predict it with whether or not a person's a male, the number of credit hours they have, and then a product between both of those, their interaction. And similarly for credit hours, we're going to predict that with male, performance, and the product between the two. So these are the equations that'll help that we're going to use to give predicted means for each of the people missing data for performance and credit hours. So let's see here. Each variable's prediction model, it can be made up of anything that you specify, right? So you can go into mice and give it all this. By default, what mice uses, not the best idea, but it says, let me look at all the missing data, and I'm only going to create models for the missing data based on the other variables that are missing as well. So mice would only predict performance with CC and only predict CC with performance by default. So it's going to make it a little bit less strict. The other part of it is that mice will also only do this, will not put in the interactions by default, but you have ways that you can go in and specify a predictive model for each variable, although that seems kind of complex. One thing I'm going to do is show you how this works from a, put down that cocktail. My handbrake cue is done. I'm going to show you the example I built in R. So this one right here. This is where talk amongst yourselves, you know. I'm going to just pull up the HTML markdown for it. There we go. Hey, I zoomed. It's awesome. Okay, so this is where we left off in the syntax. This is where the proportion was missing of each. The first thing I'm going to do is I'm going to figure out the list of people who are missing the performance variable. We're going to start with the performance regression first. Right? And here are all the people, their IDs, who are missing performance. Right? So those are all the cases where I'm going to have to impute performance to make this work. So now I can also look at the missing people who are missing credit hour production. Those are some of these, actually, there are 2% of these, or 2% of the data will overlap in both of these. So now I'm going to start by filling in all of the missing data randomly. I just literally drew, this sample is a random process. I drew a random value from the respective performance or CC variable. So this is performance, it says. Again, you're not going to have to do this by hand. This is a conceptual thing. Don't focus on the code so much, but just think what's happening here. For this group of people who are missing performance, I took a look at the distribution of performance in the data, and I drew one value at random and plugged it in. Right? Just completely randomly plugged in a value. And if my Markov chain of the chained equations work the way it should, it won't matter where I start. That's the nice thing about Markov chains. You run them long enough, they'll get to where they need to converge. One of the problems with mice is, the way it does, it's not guaranteed to. So I don't think, but I'll digress. Same thing, we're going to do the same thing for CC. So I've just made a complete data set. Now I have this complete data to start with. I won't use that complete data set. I don't want to use that as a missing data replacement right now because we just started our process. We want this process to burn in. So we're going to throw out a lot of complete data sets for a while until we get to the ones that we need to use at the very end of our chain. How are we doing? So I complete the data, I complete the interaction terms because if any one of those variables were missing, I wouldn't get the interaction. So I make up all the terms. And the first thing I do is I create a regression model for performance. And I do that by doing the linear model function. You've seen this before. We used this in the very first homework. We're actually going to use this in homework 5 as well. Performance is predicted by male CC and male star CC, the interaction. Right? I can get a copy of the betas for it. I probably won't use those. I was going to show you something, but I didn't end up going that way. But from that, I can get from each beta, here's the key thing about this process. This data itself, the beta weights for them are likely to have errors to them. Right? That regression analysis we were about to do, the betas themselves are not measured perfectly. But we know how much error is in each because we have, since we're using maximum likelihood, we could come up with an information matrix to tell us what the beta's error should be. And furthermore, we know that with ML, asymptotically, that thing will be multivariate normal. So we're going to ignore the initial betas, and we're going to draw brand new betas from a randomly normal, multivariate normal distribution. From this will be essentially a posterior draw. This is our Gibbs sample of the betas. We don't exactly know what the betas are. We know what their best values are. We don't know their distribution. So to preserve the error in the betas, we'll draw a random set of those. And with that random set, we will go and make our predicted means for each person. You can step through this code. You can highlight the values that works. But next thing what we do is we go into our data, and for each person, we go and create a predicted mean for that person. Now here is where I really should go in and show you this in R, because this is fun. Let me go show you the numbers. You may not think this is fun, but like to the amateur statistician in me, good times.
I thought you were a pro statistician.
Dude, you must not know me well. I'm just pro at being angry. That's just generally a
You need salty people.
salty. That's a good way of putting it. I'm salty. So at this part right here, I created this current data matrix that's complete, right? That was the random sample of the process. Can you see this? Do you want the bigger numbers? You're good? Okay. If you want bigger numbers, just speak up. So the first step, I created this linear model. And here are the beta weights from that model. 13, negative 0.69, 0.02, and 0.08. But the thing about it is, if I actually put summary per model init in here, you'll see that each of these beta weights has error to them. All right, so if I use these betas as they were, I would be neglecting the fact that they might not be the right values. So what I'm going to do, because this is going to be a constant Markov process, I'm going to draw a whole new set of betas from a distribution that we assume them to have in a frequentist approach. We assumed these things follow a multivariate normal distribution, and their covariance matrix is found by this right here. So I'm going to keep the error involved by drawing this new set. And that's where I get into this next step right here. You see this RMVN norm, that is a random multivariate normal. I just created betas that look like this. 13, negative 0.59, 0.01, and 0.09. You'll note that those bear some resemblance to the betas I had before, but that's the mean. The betas from before were essentially the mean of that distribution. So now these new betas I'm going to use to create my predicted means. Okay, so I do that by the following. In my data matrix, I make these predicted means right here. These right here are all the predicted means for all the observations in my data for performance, right? I don't know what they are yet. I don't know if they're missing or not, but now I'm going to go one by one through the missing, find their predicted value, and figure out the set of predicted values that's closest to that, and then draw at random performance from one of those close values. Weird, huh? We'll just work with the first person here. This is the person 1, ID 1. This is, I think, the first person that we saw on the missing list. This is person 3. Their predicted value happened to be, come on, template, 14.5, right? So 14.5 is what we think their predicted value are. I'm going to go and take the rest, and I'm going to come up with the absolute difference between this person's predicted value and all the other ones, and then order them from closest to furthest away. All right? So this is what I get. This close value right here. This is the predicted mean, how close it is, right? This is the absolute distance. So there's a bunch of people who are exactly the same predicted mean. This is the ID of the people, so I know which person's data to go grab from, right? Now, in this, you'll note there's one unique value of 0, right? The next unique value, look at all this. This is all one value, 0.011677074. These are all people that's one step away. Then we get into the next set of the next value, and then we start changing more frequently. We're going to take just the top 5 predicted means, not the 5 closest people, because that's going to depend on order. Let's take the people who have the top 5 values. That is top 5 per. These are the top numbers in that data set. Right here. These are the top values. 0, 0.01, 0.06, 0.08, 0.13. So I'm only going to take the people who have predicted means that are equal to those. Right? So now that's this set of people right here. These are the ID numbers of the people who have predicted means close to that. So now what I'm going to do is sample at random from those people. These are all, by the way, the people that should have a performance value already. Actually, they all have performance. It's in there. I'm going to grab the performance value at random and plug it into my missing data for person 3. Right. So now, my selected ID, I randomly drew person 192. I don't know what their performance is, but I'm going to take person 192's value for performance and plug it into my data. And that's what this step does. So I do that for all of my data, and I then recreate the interaction. And I've just gone through the first iteration for the performance imputation. Right? I basically swapped out all the missing data for people who had similar performance means. So now I can go over to the college credit hour production variable. This, by the way, recreates the interaction term, because when I switch one of the independent variables in there, I need to reform that interaction. So beta CC is where I'm going to save all my stuff. Again, I create this regression from our regression coefficients that go from our predicted value, right? We're predicting it with male performance and the interaction there too. Of those, give me these coefficients, but again, they have standard errors and a random value to it. So I'm going to randomly generate coefficients from their their covariance matrix and standard errors, and these are the values I'm going to use to do the same process. I'm going to go now form predicted means with that for CC. All right, the predicted means look like this. Here's a bunch of predicted means. And then I'm going to go through all the data and figure out, I have 10.51 as the first person who's missing CC. That's their predicted mean. I'm now going to go find the closest values of predicted means to 10.51. Take the top 5 from that group of people who have that same predicted value, randomly take one of the values of CC and plug it in. So here is the list of the top 5 values. You'll see that those range as well. The ID values that go with it. These are the people that are in the top 5. That's a lot of people to draw from. Right? So I'm now randomly going to select one. I'm taking person 47's value of their predicted mean, of their CC, and I'm going to plug it in for this first missing person's value of CC. Yeah, Benjamin.
Because it's random. You were talking about earlier how people were replicating studies.
Mm-hmm.
This method also seems like if you and me did the exact same thing with the exact same data, we would both come up with new missing data.
Yep.
So it's just a chance in that moment
You
in time.
bring up a good part. In a Markov chain, the more that you sample, the longer that you do this, the randomness will be roughly the same. Right? So if you're talking a p-value of 0.051 versus 0.049, yes, that could happen. The other thing with it is, and this is important in your homework, random numbers that we talk about from the computer aren't necessarily random. They're called pseudo-random numbers, meaning the computer generates a random number through a process where it starts with what's called a seed, a random number seed. So if you and I both use the same seed, R will give us the same random numbers, same string in kind of sequence. So in your homework, I actually have an option that you're supposed to turn on that sets the seed, because guess what? If I'm going to generate answers from a random data set for you for your homework, and you go do this without setting the same seed, your numbers and my numbers will be different. You'll get all red boxes even though you shouldn't. And I don't want that to happen. I know you get pissed off at red boxes as they are. I get pissed off at them too, by the way. I hate them too. But it's part of that. So yes, that could happen. The key to it though is thinking that when this process converges, it's like integrating across the distribution of what this should be. And the approximation to that integral is how many times do we sample. So if we did this 100,000 times, we should get really close to the same results, even with different seeds.
So then once you eventually are done, does it plug into the actual data set, the new number, or else you might take it out and use it in a different software?
That's exactly it. Yeah, in fact, what it does will create brand new whole data sets. Right? So if we do this 100 times, we'll have 100 brand new data sets that you could take it out and put in different software or however else. Certainly. Other questions? So this is a really elaborate story you are to make stuff up. Right? It's like if you're gonna lie, don't just tell a crappy lie. Tell a really good one. No, but here's the thing, right? They're all matched, and I just took one randomly. Sorry. I don't know that it's a lie, but this is as accurate as our prediction model will happen to be for those values. Now I can't use it. There we go. Okay, so did that for all those values. Here's the interesting thing about it. I just recreated the next step in the iterations, the prediction of performance again, going back to the first variable. And here's what you'll see. The very first line of this output where the betas from the first iteration, the point estimates, the means. In the second line, you'll see they changed. Right? This is the betas from the second one. So this is the process of the Markov chain. Right? We're going to slowly move through, and if we're doing this right, we're allowing the betas to change at each point in time until we get to convergence. The good news is, you see this function right here? Okay. That's all you have to do all that. It's just one function will do it for you. That's good, right? Not to build it yourself. But let's go back to the lecture real quick, because let me show you what it says. And this, can I get a little R hate? Can I join you in hatred for R? How many of you hate R? That's good. Jennifer, what's your website say? Do I hate R? Not today. All right, here's what it says. Digging deep into the mice help. Put that in quote, right? Is R, should they put help in quotes in R? Isn't that how it works? Here's what it says. What it will do is it will go and estimate beta and sigma by linear regression. So that's the first step that we did. It'll draw a brand new one from the proper posterior. That's the second thing that we did. It'll compute predicted values for observed and missing data from the drawn values of beta. It will find donor values with the closest predictors. That's what we did. But then it says ties are broken by making a random draw among ties. That's sort of what we did. The thing is, matching is not predicted Y, not observed Y. But the interesting thing about mice is that when it does this in the process, the betas it uses to do the draws are only based on the complete data and don't change. And so that is sort of an issue with this whole Markov process. They have an option that's not in use yet that will allow it to do as I proceed. It hasn't been built out yet, I guess. But from what I understand about mice, not entirely good. Better than single amine imputation, but I would think in the process of understanding Markov chains that this wouldn't get to where we need it to be. So it's sort of a problem. But that said, here's what we do. Here's my code. These are the distributions. So this is person one, the first person who was missing values on performance. At the end, I'm drawing 100 values. This M is the 100 samples. The iterations, mice does an iteration to mice is drawing 100 data sets. So it's going to draw 100 data sets 20 times. And on the 21st time, it's going to keep that 100. Or actually, I think on the 20th time, it'll keep that last 100 data sets as your imputed values. Right? So it's going to do this process like 2,000 times. And that's to think about getting to convergence. In the mice help guide, it says, we found convergence happens fast. Well, yeah, if you have a chunk of things that are on fixed values, it's bad. It's bad because the fixed values of using betas for only observed values, because they're based on incomplete data, they may suffer from bias if your data aren't fully missing completely at random. So that's a problem. But that said, here's person one, the first person who was missing performance. This is the distribution of the values that we imputed for them. Right? So it has a range. They range somewhere between 8 and 20. Right? Performance was a variable that in the data ranged between 0 and 20, so it's still in bounds. You'll note that the mean of it somewhere right here, it's got a little skew to it, but it's what we end up putting in for the data. So that's their values. The first person who is missing CC has this weird distribution. Right? We've got a chunk of people here, a chunk of values here. It's kind of a bimodal thing, but that's perfectly reasonable too. It could happen. Now, one thing I will note, in my syntax you see here, there is an option that says diagnostics equals true. I haven't figured out the mythical diagnostics it contains. I haven't been able to unlock those keys. That doesn't mean they're not there. So I ended up not using that. This seed value, seed equals 100, in your homework, you need to put seed equal to the password that you use to get into the system, right? Your 7-digit KU ID, right? That will guarantee that the result of this will match. But otherwise, we'll talk about that in just a moment. How are we doing? Yes, Benjamin.
If I'm understanding this clear, with all this syntax, really all we have to do is download all the softwares and kind of jump to what you just pointed at.
That right there.
Like you were just doing that to show.
I was trying to give you the concept of it. Yes. Yeah, that's it. That's the thing that does all of it for you. It's not perfect. It's not mean imputation. So it's somewhere closer to perfect than mean imputation. I don't know that there is perfect, but it's a pretty. I think it's a fairly decent way of doing it. Okay, so that gave you all the data sets. Next is the analysis phase. In the analysis phase, you need to run that linear model 100 times. And if you're like me, you're thinking, oh my God, really? Like I'm going to have to write 100 of those statements? The answer is no. When you install mice, it works with a very small set of packages to do the analysis for you multiple times. And the way that you make that work is the with statement. Right, so you say with, you tell it the data set where all the imputations are saved. This is not your original data set. This is the one that comes out of the imputation. So data 03 actually has 100 imputed data sets to it. And then after the comma, you tell it the linear model syntax that you would give it otherwise without the part that says data equals it. Right? When it does that with LM, it works. It does it for you. It doesn't take very long either. Let me show you. Let me highlight out that one. Here is the process it's doing to generate all the data. And actually, this is with the 6 variable thing. This is the process. It's going through 100 iterations of imputed data. Every 101 is called a full iteration to it. So it does 100 data sets 20 times. So it takes a little while. These are all the regressions. Anyone want to talk about something? Questions while this is going? Yeah.
I know other R packages are kind of computer dependent, like how fast or how slow it.
Mm-hmm.
Is this computer dependent with its speed?
Yeah, it should be. There are ways of speeding it up I haven't found very successfully. There's some literature in this about working with R has a built-in parallel package that tries to split up processing. I believe this works with some of it. I'm not sure, but yes, it will depend on the speed of your computer. I find the more that you do it, the better off you are. So yes, it took a while to get the imputation done, but that's part of it. But take a look. Now that I've got those data sets, data 03 is a weird thing. It's not just a flat data set. It's something called MIDS. It's a multiply imputed data set, and it's got all sorts of stuff in its object. What I'm going to do with it is create this with statement that you saw, and I just ran this linear model 100 times. Okay, that's it. It worked. But now you don't have 100 times the output. The thing that you have to do next is pool those 100 analyses together. And that's what we call the pooling phase. And in the pooling phase, we have to go in, for the parameter estimates, we have to essentially take the average value of the betas for each of the 100 data sets, right? There's 100 betas in each of our analyses. Our betas that we're going to report is the average of those. The hard part comes in the standard errors. The standard errors themselves get weighted by variance between and within, depending on what you're doing. I'll just skip that for right now. It's less important. The analysis that you can do to figure out your betas, your standard errors, your t-tests, your wald tests, and so forth, you use the pool syntax. You take the model result, you put it in the pool function, and it does this for you. If I flip over to R, you'll see what I'm talking about. Right here. So it does take a little bit of time. It's calculating this for 100, but it goes pretty quick. It's done now. And then you ask it for the summary of that pool result, and here you have it. These are our estimates of the betas, the standard errors for betas, and their p-values. So from this, we would say that there is a significant main effect of credit hours in college on math performance. There's no significant interaction. There's no significant main effect of gender. So therefore, or sex. Therefore, we have our analysis. Ta-da. Pretty cool, huh? Sort of.
Give confidence intervals,
It does. It gives you kind of the lowest values of beta. And these are not confidence intervals formed by 1.96 times the standard error. It takes a look at, of those 100 analysis, what's the lowest, kind of the low end of the lower part of it, and what's the higher part of it. So kind of a range in the middle 95, right? It also tells you things like the proportion of how much missing information affected each one of these values of the parameters, right? So you remember our data had CC, male was missing 0, CC was missing, what was it, 7 or 10% of it or something along those lines. And so the missing, but also performance was missing some as well. Actually, performance was missing 10, CC was missing 17 or something along those lines. And so you'll see that missing affected all the numbers by some performance. So what that's telling you is kind of this fraction of missing information is essentially measure the influence of the missing data on the sample variance itself. Right? So it's telling you how much missing is affecting it. So if you see really high fraction of missing information, it's telling you, yeah, you've got a lot of made-up data there. A lot of made-up. What really high is, I don't know. I don't even know that people report fraction of missing information when you do multiple imputation. Although it's probably something that would be nice to report. So, that's awesome, right? Let's take a look at the comparison. I have this one last comparison of the model without missing data. What you're going to see is, this is the using listwise deletion. Here are my results. This is using multiple imputation, and the results are nearly identical. You want to know why that is the case? Because I generated these data to have missing completely at random as their function. I, for each observation, had a 0.15 chance that it was missing, and I just randomly knocked it out if a random number for that observation did so. So my listwise deletion will give me pretty much the same thing, or unbiased estimates, as if I would have done some other fancier version for it. All right, the standard errors, roughly the same, maybe a little bit better over here, but not quite. So, point being, this is MCAR at work here. For the homework data, I have missing at random, not missing completely at random for you. I'll talk about homework in just a minute. Okay? Questions? Does this sound like something you think can be doable? It's like 2 extra functions? Maybe? Find out. There are some issues. Here are some issues with MCMC just in general. If you're using a Markov chain like we're using, you need stable estimates. So you could go and have a smaller number of iterations and not have it work the same. If you have some packages for non-normal data, it blows up. Preservation of model effects. Basically, the imputation model is important to get that correct. The other thing that's harder to do is imputation of multi-level data. It's not impossible. In fact, mice will do it. I chose to not give you that now because I found that to be a lot more complicated syntax-wise. And so your analysis will be a univariate model with multiple imputation. That doesn't make it easy because, wouldn't you know, remember how we used GLHT to get our hypotheses tests? GLHT and pooling doesn't work. So we're going to talk about that in just a second. Here's another step that's a problem. The number of imputations. This is from a different analysis in SAS using a little bit different method. But if you look at the standard, these are the standard errors based on the number of imputations I use. I mainly do this to show you that if I imputed one data set, if I did single imputation, the standard errors were a lot lower than if you move up. Oh, I love the change in light here. So, but let's talk a little bit about homework, shall we? Not that you want to hear about that tonight, but I have a homework up. I will tell you there are all of 17 questions in homework 5. A little number of questions. Not a lot, mainly because to get a really good analysis with this, it's beyond what I want you to do for class. There's too much R code and too much stuff to do. So I'm trying to minimize the impact of R on you. Even though it doesn't feel like that, I am trying. So the story, I started making this data while I was at this conference. So the story goes as follows. There was a study of attendance patterns at an educational measurement conference sessions. The goal of the study was to figure out factors that influence the number of people in attendance at the talks. I had 100 talks chosen at random for data points from this conference. And conference organizers attended each talk and recorded several pieces of data, whether or not they looked at the number of people who were in the audience. That's our dependent variable. They looked at whether or not the talk was held in the morning or the afternoon. They looked at whether or not the talk was technical or not. And they looked at the number of equations that were shown in the talk slides. Tell me if this doesn't sound like our class, right? So I came up with an analysis model that did that. It's a univariate regression, right? We're looking at two predictors that are dummy coded. I've dummy coded them for you already in the assignment. So you don't have to do any data manipulation. The data are as they should be when it comes in. Okay? Your task is to create, using multiple imputation, create 100 imputed data sets. Then use the imputed data sets in a general linear model predicting the number of attendees by all main effects and two-way and three-way interactions, the data of the time of day, type of talk, and number of equations. So now you'll have, you think about these two dummy-coded variables, there's like a 2x2 design, there's a main effect and an interaction. But then you've got this continuous variable that I want you to have interact with each of the dummy codes two-way and then have a three-way interaction overall. All right, so I gave you a three-way interaction, but I'm not going to make you interpret it that much. Promise. There's only 4 drop-down questions on this one, too. So the problem with mice, here are the options you're supposed to put in. But the problem you have to do is, because it won't allow you to use GLHT to get the effects, you have to recode your analysis to do this. So you'll actually have to run 4 models with different reference groups. Those 4 models will give you the effects like GLHT would. So when you're working this out to yourself, if you're trying to answer, for instance, the effective number of equations when the session is in the afternoon and it's non-technical, that's going to come from one of these 4 models from the dummy codes. And I would suggest that you try to write down the betas for each of those models and figure out, plug in, when the session is in the morning and technical. Oh, morning technical. Oh yeah, that's the intercept here, right? Because this would be a model where afternoon should be 1 or something like that. Point being, I think you can make it work. It's the clunky way of using GLHT. But there's an added problem in R. What I'm going to tell you for each one of these is which model to use to find that effect. Because wouldn't you know it, it should be the case that if you do it one way for one of the models, you should be able to find it from the other models as you go forward. And it doesn't do that. Yes, thank you. The pooling function or something other function in R is breaking on this and not giving us the same number. Something's not working right. Oh, I know that I can guarantee you the number of hours you spend on this homework will far be small compared to the hours I spend on this trying to get all this to work in a way that would be cohesive and not where you're pulling your hair out even more than you already have. Trust me. So I hate R with you. I'm hating R with you. So yes, I'm trying to tell you which model to look for each of these. And then in the results section, I even put the model, the effect I'm referring to up there, down here. So that's what I'm looking at. The reason for that is you could answer it using other combinations, right? Some of the questions, but it won't give you the right answer unless it matches the way I did it on my side. And yet again, another reason why with R, sometimes you get what you pay for. Questions? Okay, well, let me finish up here. If you're going to make stuff up, make a lot of stuff up.
Yeah. Put it on a shirt.
That's right. Walk around like the missing data conference with that somewhere. Yeah, that's basically it. So this is missing data. It doesn't show up in a multivariate class, hardly ever. I will tell you that if you use these methods, neglecting the fact that R seems to be clunky in a couple places, I think it's fairly established. I've seen people present and publish with these types of methods before, so if you just copy this, it should give you at least an entry point into doing missing data with your work. So that's it. I'm done. Have a good night.
So could you
Oh, question.
No, this is not a question. Could you say that this topic is missing data in most multivariate?
Oh, I love it.